and processors don't work. Signals don't travel in a processor at the speed of light. They travel at the speed of electricity in copper because that's what processors use, and that is like 1/10 of the speed of light. So basically, if a processor has to do everything in one clock cycle, like reading from memory, writing from memory, the read back stage or the write back stage or the execute stage of your data paths that we studied in the previous chapters, your your CPU cannot grow beyond a certain size unless you start allocating multiple this thing like cycles just to access memory, which would actually slow down your processor. That is one reason, and the other reason is, of course, that fast memory is expensive to build, slower memory is cheaper to build in terms of transistor density, material cost, and other such things. But at the same time, this whole hierarchy is built in a way where you try to get the performance of the higher levels and the storage at the lower levels. Basically, you want your RAM to be as fast as your cache, and you want your cache to appear to have as much storage as your RAM. So you have to create that illusion, and creating that illusion is mainly why we have so many techniques and why this chapter is so complicated. Also, the memory hierarchy is something known as a true hierarchy. Does anyone here know what a true hierarchy is? So, a true hierarchy is a hierarchy where the level below has all of the information that the level above it has. So, basically, your cache has all of the data of the registers. Your main memory has all of the data of the cache plus some more data. Your storage, your SSD or hard disk has all of the data of your RAM plus something extra. So each layer in the below layers has all of the data that the above layers possess. So this is what makes it a true hierarchy. Okay. So now jumping into the chapter. So cache memory basically is built around two concepts. All memory really is built around two concepts. One is the principle of locality, that programs access a small portion of their address space at any time, and temporal locality, that items accessed recently are likely to be accessed again. So if you have loop variables, if they are accessed recently, they are likely to be accessed again. So you should keep them in memory. And the other one is spatial locality, that items near those accessed recently are likely to be accessed soon. So the biggest example of this is, of course, arrays. If you access element 1 of an array, the chances are very high that you're going to access element 2 very soon. And if you access element 2, then element 3 is likely to be accessed, and so on and so forth. So if you are running one line of code of one program, then the chances are very high that you will run the next line of code of that program before jumping to something else. So spatial means location. So location wise, whatever data is stored near the previous data is likely to be accessed, and temporal wise is that timing, that anything that you accessed recently, you are likely to need to access it again. So yeah, we build our memory to take advantage of these two localities, temporal and spatial locality. So we create a hierarchy, we store everything on the disk, and we copy recently accessed and nearby items from the disk to the smaller DRAM memory, which is the main memory. We copy more recently accessed and nearby items from the DRAM memory to the smaller SRAM memory, which is a cache memory that's attached to the CPU. So basically, your hard disk or your SSD has all of the data that you ever run on the system. It has data programs that you may not be running on a daily basis also. Whereas your RAM generally has fragments or parts of programs that you are running regularly or that are currently running, right? So these are aspects that you have to take care of. And then the cache has the data about the current program that you are running. If you have lots of RAM, it's possible to have like many multiple programs stored in your RAM and running in the RAM at the same time. But your cache is typically concerned with having the data of the current application that you're running, because the cache is very small, right? Cache is a few tens of megabytes across L1, L2, L3. So unless your programs are very small, it's not possible to fit multiple programs onto the cache. So now you have to remember the hierarchy. Okay, so one is the memory block or the memory line. So these terms are interchangeable, and you should know them all, because sometimes you might see questions, or some professor or some interviewer asking you about cache lines. So cache lines are nothing but blocks, and one block is nothing but one unit of access. So we previously learned about word addressed memory versus byte addressed memory, right? So byte addressing is when you copy one byte, address one byte at a time. So when your processor accesses one byte at a time, it's a byte addressed memory. If a processor accesses anything more than one byte at a time, like let's say it always pulls 4 bytes at a time, so that 4 bytes is one word, because basically that one word represents the unit of data for that processor. That processor does not see the data uh, at the byte level. It sees the whole data at the four byte level, a 32-bit level. So that's a word address processor. So it represents basically how much data is copied at once in one operation. It can be multiple words also. It can be one word also. So if the access data is present in the upper level, it's a hit, like the data is successfully hit. If it's unaccessible, it's a miss. Basically, if your data is there in the register, it's an immediate hit. Otherwise, it's a register miss and it goes to cache. If it's there in the cache, it's a cache hit, and the data is served from there. Basically, a processor is looking for certain data to do the next stages of computation, right? So if the data is available in the cache, then the processor will just use the data from the cache. Why would it go to RAM where it takes like hundreds of cycles for it to get the data? But if the data is not there on the cache, then there's a cache miss, and the processor has to request for the data to be sent to from the main memory. And then in the main memory also, if it's not there, then it's not a main memory. A main memory fault has data that is not found in the main memory is pulled from the secondary memory if it is there or not, but there is a specific term for that. Anyone knows? The hint is you've heard all of this word before, basically. If your processor tries to access data that's not present in the main memory, what is it called? So it's called a segmentation fault or a seg fault. So yeah, that's where the term came from, and it's the original use of the word seg fault. So it's something worth knowing. So basically, at each level, the processor tries to access the data from the highest level possible. It tries to do that as far as possible, that whatever data is available at the highest layer, it will just get it from there. It will only go to the lower levels if it's not available. Okay. So memory technology has varying costs. This is of course the time from when the book was published, but it's not too different from the prices now. So the costliest kind of memory is static RAM or SRAM, which is what is used in caches. It's expensive for a multitude of reasons. One is that it's very fast, and the second thing is it requires a lot more silicon to manufacture. So memory chips are made of something known as bit cells, which are what hold the unit of data. So basically, an SRAM chip requires 6 transistors to store 1 bit of memory. whereas dynamic RAM, which is not static, requires only one bit or one transistor per unit of storage. So the problem with SRAM is again because it requires six transistors is that it takes up more space, and because it takes up more space, it is less dense, and because it is less dense, there's not a lot of it. So I mean, there are trade-offs. Dynamic RAM is what you normally associate with the term RAM. It is your main memory, unless uh, the data has to be refreshed constantly. So, all of you learnt in school or college that as long as RAM is powered on, the data stays, right? So, how many of you understood that to mean that if I keep my computer on for 1 hour, then the RAM has to just stay powered on, there is no refreshes and all. Does anyone know that the RAM has to be refreshed periodically for the data to stay there? Any guesses on what that refresh time is?
I don't know about that much, but I don't. I know about it is capacitor based, so due to leakage current, we need to refresh it.
Yeah, and you need to refresh it pretty fast actually. It's usually a few tens of times per millisecond. So yes, the data is dynamically stored, but is not in the sense that as long as the RAM is powered on, the data will be there. Even if you just supply power, it's just supplying power is not enough. You have to refresh it, and I think it's like something like 133 times per millisecond or something. And there are, because of this refreshing nature of RAM, there are certain attacks that take advantage of the RAM being having to refresh this way. There are like row hammer attacks and stuff. So dynamic RAM is much more capacious than static RAM. You have 24 GB DIMMs. I'll tell you what a DIMM is also. A stick of RAM is called a DIMM, which stands for dual inline memory module. I'll tell you what that term also means, but it's about 10 times slower than static RAM. So, if 1 nanosecond is 1 gigahertz processor, then you've already gone from one cycle to needing 50 cycles for accessing DRAM. And magnetic disk is 5 milliseconds to 20 milliseconds, which is HDD. If you go for SSDs, the shittiest SSDs are about 4 5 times faster than hard disks, and even very fast SSDs are no more than 10 times faster. So basically, if the secondary memory where all of the programs are stored, it represents millions of CPU cycles, because 1 millisecond is 10 power 3, right? And 1 nanosecond is 10 power 9. So 10 power 6 difference is 1 million or 10 lakhs. So 10 lakh CPU cycles. It's shit slow. So the ideal memory is a memory that has the access time of SRAM, which means that it takes only a few nanoseconds to access, but it has the capacity and cost per gigabyte of magnetic disk. Of course, such a memory does not exist, so we have to fake the effect with the hierarchy. So DRAM is stored as charge in a capacitor, which is a single transistor that's used to access the charge. It has to be refreshed very often, and bits in a DRAM are organized as a rectangular array, as you can already guess. So the DRAM accesses the whole row at once. So this takes advantage of your locality of the spatial locality. It accesses all the data at once, and this row access is also why array data structures are very fast, because you access all of the data is also stored in a row, and you access the entire row at once. So it saves you a lot of CPU cycles. So RAM also supports something known as a burst mode, where you supply successive words from a row with reduced latency. Modern day RAM is all DDR, double data rate. So if you represent the rising and falling clock cycle, so again, In the absence of a whiteboard, we'll take the help of our good friend MS Paint here, and we'll zoom in to something. So let's say, yeah. So a digital signal looks something like up, down, up, down. Obviously, these lines are all meant to be straight lines, but right. This is 0 and this is 1. So this is the rising clock edge. Like here is where the signal is going from 0 to 1. And this is the falling clock edge where the signal is going from 1 to 0. So just like there is DDR RAM, there is also SDR RAM, although it's not used any longer. So SDR RAM only updates the value when it's going up. So this counts as one update, and then this is not counted, then this counts as one update. Then this is again not counted, this counts as one update. This is not counted, this counts as one update. Obviously, you're wasting half of the bandwidth. So DDR stands for double data rate. So this is counted as one update. The falling clock edge is counted as one update. Then this is already one, and this falling one is also counted as one. This rising one, and then so basically it's double. Okay. There's also QDR, which has separate inputs and outputs, but that's not important. All RAM today is DDR. So DDR stands for double data rate, and the RAM itself stands for random access memory. So all of the RAM today is DDR4, 5, DDR6 is coming out. So each of these have numbers associated with them, which is the clock speed of the RAM itself, like 5000 megahertz, 6000 megahertz, and something known as the cache latency, which is how long it takes. So you have CL16, CL13. So this cache latency is the second number associated with RAM, and it's the number that people know lesser about, but it's just as important as the speed, the capacity. So this cost of RAM has been falling for many generations, and although now it's again rising due to HBM being the only type of memory that's being produced. So in the modern day, LLMs are consuming something known as high bandwidth memory, and high bandwidth memory is memory that is supposed to have a very high bandwidth, as in you can supply a lot of data in parallel at once, and it consumes a lot of silicon, and silicon is the reason why that silicon is the reason why you can't find RAM to build a PC anymore, or it's getting really expensive. So RAM has a few performance factors. One is a row buffer, which allows several words to be read and refreshed in once. A synchronous DRAM, which allows for consecutive accesses in bursts without needing to send out each address. And you have banking, which allows simultaneous access to multiple DRAMs at once. So this banking is the reason why instead of putting 1 GB stick of RAM, it's usually recommended that you should have 4 plus 4, right? Because you can then access data from both of them at once. So it kind of doubles your bandwidth. So always having matching sticks or matching amounts of RAM. So it's kind of important. Again, so RAM also uses a technique known as interleaving, which means that you can, like, let's say that you have data that you want accessed. So you can take advantage of one fact that the memory is interleaved. Like you can store half of the data at the top at one RAM stick, and the other half of the data on the other RAM stick. So your processor can basically access both of them together. So you get the data in half of the time. So secondary storage is flash. So flash is usually made out of NAND flash, which is bit cells which are like NAND gates. It's non-volatile. It is These are what your modern day SSDs are made up of. And this is 10x to 100x faster than disk. It's smaller, lower powered, more robust, but it costs more. So the reason it's more robust is again it has no moving parts, unlike a HDD. So NAND flash is used because it's denser, it's cheaper, and it does wear off. So SSDs spinning rust or hard disks technically would survive forever if there's no other damage, but SSDs do wear out. Although the wearing out takes a long time and bigger drives wear out much slower than smaller drives. So it's in reality it's likely that you'll buy a new computer or change your drives much before it wears out. The disk storage is based on the hard disk, of course. This data stored in cylinders, sectors, and tracks. It's like multiple CDs stacked on each on top of each other. Both of these use something known as ECC, which is error connecting codes. So there are questions that are sometimes asked about Hamming distance and other such concepts in error correcting codes that are important. And so, like this is an example, like you have a 512 byte sector in a hard disk. It rotates at 15,000 RPM, 4 milliseconds average seek time, 100 megabytes per second transfer rate, and this is a controller. So you can do math on it to calculate that what's the average time needed to read something, right? So there's a lot of issues with hard disks. One is that manufacturers quote average seek time, and that average can means nothing because almost everything in hard disk depends on when you access the data or what data is accessed at what point. Two pieces of data can be fragmented across the disk. That's why defragmenting disks is a thing, which means that over time it's possible that one piece of data is stored on the top of the first disk, another piece of data is stored on the bottom of the third disk. Process of defragging your drive is literally moving all of that data together into the same area. So there are disk controllers that allocate all of this data. So there are multiple disk controllers that try to improve how the data is accessed. Previously, there was SCSI, which is a small computer single interface. Then we had ATA, which stands for Advanced Technology Interface Attachment, and now we have SATA, which stands for Serial Attached Technology Attachment. And SATA is the current standard for hard disks. So now we come to the most interesting part of the memory, which is the cache. Now this is important because it is the most interesting part of the memory because it sits right between the processor and everything else that's going on. So all of the algorithms, all of the clever hacks, and all of the techniques that are done here only. Because it's the closest level of memory hierarchy known to the CPU. So one thing is that how do we know if the data is present? And the second place is where do we look? So caches are something known as content addressed memory. Okay, so content addressed memory is different from an normal addressed memory in the sense that the name only gives it away. The processor does not look for memory addresses, it looks for data. Okay, so here you're looking for data. Basically, if searching for somebody's like normally if you have to go to somebody's house you search for their address, or if you have to locate certain information you have to go to that address, but if you are searching for a person you need to find search for that person. So in content addressed memory, which is a cache memory, you are looking for a piece of data directly. You don't care where the data is stored, you're just looking for the data, right? Because the data might be stored anywhere in the cache. So one is a direct mapped cache. Okay. where the location is determined by the address. So direct mapping means that a particular piece of information can only be present in one place. Either it is there in that place or it is not there. It's a binary choice. So, like you have powers of two, okay, and you use the lower order bits. So you say that everything that is like, for example, you are using powers of two. So all of the data of a particular type will be divisible by that number. So if you have a block address of say 51, and there are 50 blocks in the cache, okay, so block address, so if a block address is 51 and there are 50 blocks in the cache, it will be stored in location 1. Okay. If there are, if the block address is 49 and there are 50 blocks in the cache again, then it will be stored in location 49. So again, the problem here is that you have a lot more data than the number of blocks in the cache. So address number 50 will be stored in 50 divided by 50 block number 1. Address number 100 which will also give you a modulus of 0, that will also be stored in block number 1. Address number 200 which is also a modulus of 0 with 50 will be stored in block number 1. Similarly, if you have some other number like say 49, so 49 modulo 50, like okay, 51 modulo 50 is 1, the remainder is 1. So the problem here is that any number that gives you the same result at the end of the modular division will be stored in the same block. Okay. And you cannot store two numbers in the same block. So the only thing your cache has to do is it has to remove the old value and add the new value. So this is a direct mapped cache. So how do we know which particular block is stored in a cache location? You store the block address as well as the data. You need only the higher order bits, which is called the tag bit. So if there is no data present, you can put a valid bit as not present, which is 0, or you can, if the data is present, you set it to 1. So so here's an example. You have 8 blocks, for example, which means 8 blocks can be like either like 4 bytes each or 2 bytes each. It depends on how much you choose your word size to be. Here, let's assume you're storing one word per block, which means just one value per block, direct mapped cache. Say your address is 22. So in binary, that's 10110. So it has to be stored in because you have 8. You have to do 8 and 8 divided by modular division of 22 divided by modular division of 8, which will give you 6. So it has to be stored in 6. 110 is 6. Okay. So 110 is 6. So it has to be stored in the sixth block. Sixth block as in, actually the seventh block because it starts at 000 instead of 001. So it's stored in the second last block, which is the block number 6, starting when in a range that goes from 0 to 7. The valid bit is turned on to true, and the tag bit here is 10, which is the upper two bits of the 10110. Okay, and the memory location is 10110. So if your address is again 26, so 26 modular division 26 modular division by 8 is 8 threes are 24, and then 2 is left, so you store it in 2. Now the tag upper two bits are 11, so you are storing 1. So are you seeing this? So by just storing the tag bit, you are saving storage. Like you can reconstruct this address just by putting these 2 bits in front of these 3 bits. So here also you can put these 2 bits in front of these 3 bits, and here also you can put these 2 bits in front of, so anywhere. So 22 or 26. Now let's say you have 16. So 16 divides neatly by 8. It will give you 0. So here your tag bit is just 10 because you'll get one trip. 16 represented in binary is just 1 with 3 zeros. So your index is 3 zeros and the top 2 bits are 1 and 0. So again, with with no modular division is, so every time, just if you want to compute the exact address, all you have to do is take those upper 2 bits, which are the tag bits, and place it in front of the index bits, and you reconstruct the entire address. So splitting the address this way into index and tag, it saves data. Like, you don't need to store the entire address again twice. It's for storing, saving information. Okay, so there is a valid bit which tells you if the data is there or not. There is a tag bit which is the upper two, in this case, upper 2 bits, because upper 2 bits can uniquely identify the data in this case. If the cache is bigger, then you will need more than 2 bits, and then you have the data, which is the rest of the lower order bits. Okay, so you have, let's say you have 64 blocks and you have 16 bytes per block. So how much data can you first of all store in this cache? If you have 64 blocks and 16 bytes per block, you can store 64 into 16 bytes. So in this, it always helps to convert it into standard units. So you have 2 power 8 blocks and you have 2 power 4 bytes. So 2 power 4 into 2 power 8 is 2 power 12, and 2 power 10 is 1 kilobyte. So 2 power 12 is 4 kilobytes. So this is a 4 kilobyte sized cache. So to which block number does address number 1200 map? So it's 1200 divided by 16, which is again modular division you need to do. So the division, it's 75, and so first you compute the block address, because each block is 16 bytes, right? So you have to first figure out what's the block number. So you figure out the block number by dividing 1200 by 16, which gives you 75, and then you figure out which block that will map to, because you have only 64 blocks, so it maps to 11. So then your tag will have the top 22 bits, index will have the middle 6 bits, and the offset will have the last 4 bits. So this is how you represent the number in the cache. Okay, so now the main question comes is, okay, we have this block size, we saw a bunch of block sizes, we saw a block size of 2, we saw a block size of 4, we saw, now here the block size is very big, it's 16 bytes, so it's like 8 into 16, it's like some really big number, like 128 or something. So I'm storing like 128 bits of information in one block. So how should I decide that block size? So block size has a few considerations. One is that a larger block size reduces the miss rate, because spatial locality, you are accessing more of the data at once, right? So if you have 128 bits, or 16 whole bytes, you can store like 4 elements of an array together. So array accesses are faster. But the problem is that if you have larger blocks, you will have lesser blocks, because if you have 4 kilobytes of storage only, uh, if you had 8 byte blocks instead of 16 byte blocks, and you had 64 and 4 kilobyte cache, then in 8 byte blocks you could fit 128 blocks. But now you can fit only 64. Now if it was 32 bytes, then you could fit only 32 blocks. So the number of blocks is lesser. So this means that there's more competition. Like, the modular divisions denominator will decrease. So the chance, like for example, if you have only 2 blocks, for example, every single second number will map. 0 will map to block 0, 2 will map to block 0, 4 will map to block 0, 6 will map to block 0, and every second number from 1, 3, 5, 7 will map to block 1. So this means that your cache will keep on updating the data again and again and again before it is accessed, and the miss rate will increase. So the miss penalty will increase, because again you have fewer blocks, right? So block can't be too big and the block can't be too small. Both are problems. So cache misses, when the cache hits, the CPU proceeds normally. Basically, if the data is there in the cache, it proceeds normally. But if it misses, then the CPU has to stall the CPU pipeline, fetch the block from the next level of the hierarchy, and if it is an instruction that was missed, because again we have von Neumann computers, right? Data and instructions. The next piece of information that the CPU needs can be anything. It might be an instruction, it might be a piece of data. So instruction means you have to fetch the instruction. If it's a piece of data, you have to complete the data access. So now we have a problem that let's say that the processor got some data from the cache, okay, and it did some maths on that data, and now the data has an updated value, and it writes that data to the cache. So now my problem is my RAM also has that data, and my hard disk also has that data. So the value of the data in the hard disk and main memory is different from the value in the cache. So my data is inconsistent. So how do I solve the problem? Any guesses? Did anyone understand the problem?
Yeah,
Yeah.
during the write
Yeah.
operation, whenever we are doing the write operation, we have to do two operations.
Okay. But tell me one thing, if I'm always writing to main memory when I am writing to cache, won't my cache access be limited by the speed of main memory?
We can do one thing
I
whenever we are removing the data from RAM.
Hmm.
Whenever we are removing the data from RAM, that time we will update the main memory. Otherwise, no, we don't have to do.
Not removing from RAM, removing from cache.
I mean, whenever we are
Yeah.
removing data from cache, that time only
Yeah.
we do the write operation.
Yeah, so one option is what Deval said. It's a good option because, like, let's say that you have to do maths on the same data many times. So, like, let's say that some variable I is there, I becomes 2, then I becomes 3, then I becomes 4, 5, 6, 7, and it goes on till 1000. And finally, then that value of I is not needed anymore. Then to the main memory which stores the final result of the computation, it does not matter whether I went through 999 different values. Only the final computation is important, right? Because processor is always, so this means that you have to do one thing. The processor should always get all of its data from cache. Processor will not bypass the cache and get the data directly from the hard disk or from the main memory. This thing is, if you want to only pull data from the cache, the condition is that if there is a cache miss, okay, then the first step is bringing that data into the cache, and then the processor tries to get the data from the cache again. So the cache, the hit rate has only the time for a cache hit in the calculation, but the miss penalty, it includes the time for the cache miss itself plus a cache hit, because first you have to get the data into the cache and then you have to access it, and you need this because of this write through scheme. So here one problem is that if you write through, which is what we discussed, Deval said first, that every time you write data to the cache, you also write data to the main memory. Then the problem is that your write will take longer because you cannot, your processor only has to do the job of writing the data to the main memory. So if your main memory is 100 times slower than your cache, your processor cannot proceed until that write is complete, because otherwise the data will become inconsistent or there's a chance of becoming corrupted, right? So one is you create a buffer, and some hardware does use buffers like this where you hold data waiting to be written to memory. But again, if this buffer overflows, you're in deep trouble. So the other option is that you write on demand only when write back. So keep a track of all the bits, whether a data bit is dirty or not. So here, dirty means if a data bit has been changed, then it is dirty. If it has not been changed, it is not dirty. So basically, if it is being hit, like if it is dirty, Then when you are writing back, flushing the cache to bring the next batch of data, that time you have to update the data in the main memory. So this is much more efficient, and this is what is used a lot. So write allocation. So what should happen on a write miss? So there are alternatives for write through, which is like updating the main memory and the cache at the same time. One is allocate on a miss, which is fetch the block, or write around is don't fetch the block. So we usually fetch the block. So one example of this is the Intrinsity fast math processor, which this book uses a lot as an example. So it's an embedded MIPS processor that has a 12-stage pipeline, and there are instructions and data accesses on each cycle. So it has a split cache, which means it has a separate instruction cache and data cache, uh, uh, and each is 16 KB. So not a lot of processors have split caches these days, but some of them do. And basically, the miss rate in this for spec benchmarks, for example, is 0.4% for the instruction cache and 11.4% for the data cache, which is a very small number. So it really makes you think that what kind of crazy engineering did these people do that with a cache of 256 16 kb you are able to have a hit rate that is this high on when you have like several gigabytes of RAM. Like it makes no sense, right? Like you have a RAM that is 16 GB, 32 GB, 64 GB, or even 4 GB, for example. Your cache is less than 1 by hundredth of it's 1% of the size of the bigger memory. Yet 99%, 90% of the time the data that you need is there in that 16 KB. So how do you pick which 16 KB to put into the cache? That's what the entire field of performance engineering is about. So main memory is used to support cache. So we use DRAM for main memory, which is a fixed width. So for example, if you have one word wide DRAM, then the miss penalty is 65 bus cycles for this example. If it takes this much, so you can measure the cache performance in a few ways. One is how much is the hit rate, how much is the miss penalty. You can use these formulas: memory access by program into miss rate into miss penalty. So here they've done a calculation with one of the processors. So if your cache always would hit, then your processor's ideal computation time would approach the theoretical limit. But even the hit time is important. Now you would say that how can you manipulate the hit time, because it's a hardware thing, right? You can't control how fast the processor will fetch the data, but you have to remember that nowadays processors have multiple caches, and the L1 cache is much faster than has a hit time lower than the L2 cache, and the L2 cache has a lower hit time than the L3 cache. So that hit time becomes important because if you have very low hit time, then you can afford to take some penalties. If the hit time itself is very large, then you'll have problems. So when the CPU performance is increased, the miss penalty becomes more significant, uh, uh, because again your processor is spending more cycles. Your processor can go through more cycles, so it's more important. It decreases the CPI. You can't neglect cache behavior. It's very important. So there are things known in cache is known as associativity, which is like where you can store the data on the cache. If a cache is fully associative, you can store any data anywhere in the cache. If it is n-way set associative, then you can store data at any place within a set in the cache. And if it is direct mapped, then you can store the data only in one place. So for example, here let's zoom in. So for direct map, you have 0, 1, 2, 3, 4, 8 blocks. And a piece of data can go only in one of these blocks if for a particular address. Basically, if it depends on the number of blocks, as I said. And here we have grouped them into four sets. Okay, so set 0 and 1, 0, 1, 2, 3. So data can either go in row 1 of the 0 block or row 2. If I tell that the data is in set 1, set 0, it can be in either of these two locations. If I say that the data is in set 1, it can be in either two of these locations. Set 2, either of these two locations. And here the associativity is 2. So associativity is also called way. So n way. So four-way cache means the associativity is 4 and each set has 4 elements. And then there is finally fully associative where any data can be stored anywhere. Okay. So for a cache with 8 entries, a direct block is block 0, 1, 2, 3, 4, 5, 6, 7. Two-way means you're splitting it into two. Four-way means you're splitting it into two sets with this thing. And finally, eight-way is fully associative where any data can be stored anywhere. So this determines this associativity impacts like how what the hit rate hit like miss penalty is, how much data can be stored, and what how it works. So, so four block caches. So here we are taking an example with four blocks. So direct map two-way set associative. So block sequence is 0, 8, 0, 6, 8 here. So 0 is there in the memory. We put it on block address of 0. Now 8 comes. So 8 is also divisible by 4. Okay. So 8 will also be stored in address 0. And now next we want to store check if the value of 0 is there in the cache again. The value of 0 is no longer there in the cache. Why? Because unfortunately the previous value of 8 overwrote the 0. Then you have 6. So 6 will be stored in 2. And then you have 8. So direct mapped is very bad because the replacements are very frequent. Then you have two-way set associative where okay, if you have 8 and 0, then you have two places to store them. So 0 modulo 8 is 0, so you store it in address 0 in set number 0, and 8 modulo 8 is also 0, so you can store it in the first set again because each set will have two values. So it's more forgiving. And fully associative, the advantage is that even if you store 0, 8, 16, 32, all numbers which are modulo 0, you can just store them at different locations. So fully associative is nice because you can store any data anywhere, but the penalty is that again it's expensive to construct because in direct mapped, the hardware to find where the data is very easy. Okay. It's very easy because you can just directly like look for that address and check if the data is there or not. For set associative, you have to do two steps. First, you have to check if it is there in that set or not, and then in that set, which location. It's fully associative. The problem is for each and every single data access, you need to search the entire cache. And searching that entire cache, either it is slow because you have to search one element at a time, or it is expensive because you have to build special hardware that can compare all of the values in the cache all at once. So increasing associativity rate decreases the miss rate, as I explained, because you can store more data without having to replace it. So one-way cache is 10.3 miss rate, two-way is 8.6, four-way is 8.3, eight-way is 8.1. So usually what we've noticed is that even though fully associative is ideally you want fully associative, but even going from direct map to two-way or four-way is very efficient because the way data is organized, that even giving like two or three options for similar values to be stored is often enough. After that, it's a point of diminishing returns. Okay. So one is the replacement policy. Okay, that how do you replace the data in the cache? So in direct mapped, you have no choice. In set associative, you have no choice because the data can be stored in only one place. For set associative, you prefer non-valid entry. If there is one, otherwise choose among the entries in the set. Basically, if some data is already stored in one location, you pick the other location. Otherwise, you choose among the entries. If you have to choose, like, okay, should I store the data in the area where the previous data was stored? One option is that, like, let's say that you have 0 and 8 stored in block number 1 because it maps to modular 0, and then 16 is coming. So the slot number 1 of set 1 is also full with 0, and slot number 2 is also full with 16. So then you have to choose which one to replace because you can store two values there, right? So you use LRU, so least recently used. So which of the numbers has been accessed less frequently? You choose that. So you can either use LRU, but problem with LRU is you have to track, like, which means that you have to figure out which data was accessed when and all, right? And building the tracking is also not easy. So sometimes some processes legit use random sampling. So this gives some good performance, but the main good thing about random is there are no corner cases. Like for LRU, you can come up with a series of data where it just misses every time and the performance is horrible. But for random, there are no edge cases because it's random. So these days, processors have multi-level caches, which is a small primary cache attached to the CPU is the first one, level 1. Level 2 cache is the cache that sits above level 1, and it is slower and it's faster than the main memory. And then level 3 cache is there, which sits on level 2, this thing. So you can do a interesting experiment on this. You can try to. There's a way to actually write C programs for this. You can write a C program to read data from an array, okay, of a particular size, and you can write a program that you can figure out where the cache boundary is. Basically, if your array is a certain size, the reading and writing from the reading from the array will be really fast. Beyond that, you'll notice that the speed is a little bit slower at certain point, and then again it will become even more slower. And beyond a certain point, the access will take even more time. So those are at the cache boundaries. If all of the data of your entire array fits in level 1 cache, then accessing it is very fast. If it fits in level 2 cache, then it will be slower than a level 1 access, but it won't be as slow as L3 axis. Then again L3 axis, and finally when you move beyond L3 axis, then yes, the entire array has to be fetched in pieces from the main memory. So you can actually write a program to figure out how big your cache is from that. So here they've given an example. If it's one clock rate is 4 gigahertz, one cycle per instruction, the miss rate is 2%. With just primary cache, your CPI is 9. Now, if you add in level 2 cache, which has a higher access time, it's slower. And but the global miss rate is lesser. The miss rate is lesser because the level 2 cache is bigger than the level 1 cache. It can store more data, right? So the miss rate will be lesser. So, but the problem is that the hit time is also higher. So this has improved your performance by a factor of almost more than 3. So when you build multi-level caches, you have to worry about a few things, and this is where truly we're getting into the heart of multiprocessor design. Is that your primary cache has to focus on hit time. It should hit as fast as possible. Your level 2 cache focuses on lower miss rate. So hit time is less important because it's okay if it takes a few extra nanoseconds. It is still much better than the like requiring 50 cycles, which the main memory requires. So L1 cache is the closest to the processor, and it has uh, a higher distance. So let's take a look. L2, L3 cache processor. Let's see. I can show you an image of a die here, CPU die. Okay, so let's make that bigger. Open image in new tab. Hopefully, it's a high enough resolution image. Okay, that this will do fine. So this is a modern day processor. So here you can see that there are 4 cores, and okay, so each core is there, and next to just above the each core there is the L1 cache. It is like literally attached to the processor. The L2 cache is a bit further away, and it's bigger in size. And finally, there's the L3 cache, which is shared among all of the cores. So even the physical distance from the die of the processor differs. Okay, so L1 cache is smaller, and L1 cache is block size also smaller. So out of order processors, which superscalar processors, which can execute instructions in orders different from the instructions given by the compiler. Compiler gives you instructions in one order, but the processor can execute those instructions in a different order. So out of order CPUs can execute instructions during a cache miss. They can make speculative loads and stores. So pending store stays in load store unit, and dependent instructions wait in the reservation station. So effect of a miss depends on the data flow of the program, like how it is written and all that. So misses depend on memory access patterns, and memory access patterns are why certain data structures are favored over other data structures. How exactly the program accesses the memory is kind of important. So here is a comparison of radix sort, quick sort, and quick sort. So here it's showing size k with k items to sort, going from 0 to 4096. So you can see that quicksort does not blow up so much. Like the instructions per item remains largely constant. The quicksort has more stable behavior, whereas radix sort initially it requires more instructions. So initially it's not so fast, but as the size increases, like if we go beyond the point where the data can fit in the cache, then radix sort becomes much faster. Okay, so, like this is just an example of. So here we have instructions per item, which is the number of CPU instructions, assembly instructions per item of data access. Here we have clock cycles per action, and here is the cache misses per item. So quick sorts, cache misses start increasing, radix sort also increases, but ultimately instruction clock cycles per this thing wise, radix beats out quick sort for very large number of items. So this is an example of how literally the algorithms you choose can perform differently based on cache patterns, and often this difference is so big that even certain data structure choices become more important than the raw algorithm choice. Like there are some cases, I think there's one specific case where some variant of bubble sort or some variant of insertion sort is used over some variant of faster quick sort or merge sort because it's cache friendly. So it depends on algorithm behavior and the compiler optimization for memory access. So you can also do software optimizations via blocking, which is by designing the data to be accessed in blocks. So the goal is to maximize the access to data before it is replaced. So consider the inner loops of DGEM, which is double general exponent matrix multiplication. So normally it's just your like that, But instead of that, you can choose to access the data in blocks at once. So here you have defined hash, defined block size as 32, and then you've defined a function, and inside that function you are incrementing it in the sizes of the block size, and you're doing the computations keeping the block size in mind. So this program will run faster. It will run quite a bit faster than the unoptimized one. So you can see here the unoptimized one gives about 1.7 G flops at 32 into 32, but at 960 into 960 size array, where 960 into 960 elements, it drops down to only 0.8 G flops. So the blocked program, where we take the block size into consideration, it performs at the same speed when the array is very small, because the entire array fits in the cache, so it doesn't really matter whether you're accessing it at block size or level or not. But as the block size level grows to, I mean, as the array size grows to a point beyond what it can fit in the cache, then blocking gives you about twice as much performance as just like raw dogging, like, no optimization wise. So dependability is again dependent on, like, first of all, were you able to deliver it the data or not, and the second is how much deviation there was there. So I think this is a natural point to stop today, because